Hi everyone, thank you for coming to my presentation seminar today. Before I begin, I'd like to express my gratitude to my supervisors. I'd like to have been there right from the beginning, every step of the way. Rich and Anne, who joined the panel a little later, but have been very helpful. Thank you very much. I'm very grateful. Okay, so the title of my PhD is Enlightening Science, Addressing the Cognitive and Non-Cognitive Aspects of Science Learning. So any one of you think that science is not important? Okay, so we all agree science is important, right? Because if you have science literacy, you can explain about the food that you eat, the digestion, the transportation system that you take, the technology, weather, nature, and even the urban city that you live in. Science is part of STEM and it's been said to be the future of all knowledge-based economies. And even in Australia, there's talk about investing in STEM studies for the continued prosperity of Australia. And recently, they mentioned about science and innovation being recognized internationally as key for boosting productivity, creating better jobs, enhancing global competitiveness. And 75% of fastest growing occupations now require STEM skills, and the demand for STEM just continue to grow. And part of Australian government's initiative is for more students to take STEM subjects in higher education. But is this easy? Not really, because science education is in crisis. Students lack aspirations to pursue science-related education and careers. And a decline in science enrollment means a shortage of science graduates, science teachers, scientists, and even science literate citizens. And even the closure of science departments in some countries. And when we have less science literate citizens, there's reduced engagement in science-related issues and decision-making processes, which will threaten global competitiveness and national security of the country. Physics, which is the focus of my PhD, is also in crisis around the world. And when we look into what is going on in the classrooms, we see traditional instruction being the main mode of pedagogy. Students are passive learners and the teachers transmit information. There's a disregard for cognitive processes and student motivation is ignored. Okay, let's look at student cognitive processes. For those who listen to me doing my 3-minute thesis, you somehow have an idea. Like right now, you're all paying attention to me presenting, so you can't remember everything because your working memory is limited in capacity and duration. So most probably just get the gist of it. But if you pay attention, and then the cognitive processes will happen. So if I present everything within the capacity of your working memory, then it gets stored to your long-term memory. And next time you see me, oh, this is the girl who did a PhD on science education. But if you are not interested, you've been forced to come here, then you will not have attention at all. And we know students, and you guys as well, if you don't pay attention, no cognitive processing will occur and you will not learn anything at the end of the session. So the issues with physics learning is that it is known to be complex and difficult. Anyone of you think that your physics education in school is such a breeze? Anyone? No, because physics itself is a combination of conceptual and procedural knowledge. That means you need to know the concepts, the science concept, and you apply procedures to solve problems. So basically this conceptual and procedural knowledge interact, causing too many interacting elements that overload your working memory, inhibiting your learning, so you don't learn much. And when you don't learn much, you will not succeed in examinations, and then you lack the self-belief, and you will lack the motivation to continue pursuing science-related careers and subjects. So research gaps, of course science education has been looking into this, but they mostly focus on studies, how do I improve students' understanding of forces, for example. They focus on the cognitive part and it doesn't look much into motivation. And there's also lacking constructs to guide instructional design for optimizing learning. And intervention studies normally focus on just one aspect, to how to make students motivated or how to improve their cognitive processes. So we have a child maybe who's already motivated, engaged, eager to learn, and then it goes into the physics classroom and we do not look at the cognitive processes and they experience cognitive overload, and over time lower chance of achievement, and then they will end up being motivated, lower self-concept, and inattentive to instructions. And when they start to be inattentive, we know that they will not learn. So the overarching aim of my thesis is to address the cognitive and non-cognitive aspects of science learning by looking at student motivation, achievement, and the learning processes that contribute to the achievement. And I do this through a series of studies. Studies 1 and 2 look at student motivation and achievement, and studies 3, 4, and 5 look at element interactivity and motivation. So at the end of study 2, I'll take a break and explain to you more about element interactivity so you can understand my studies 3, 4, and 5. So study 1 and 2 is something all of you are very familiar with. It's just looking at motivation and achievement, so I'll go very fast on this one. The participants are grade 7 boys and girls. It's not big sample size because I do it in one school. In Singapore, they're about 13 years old. They are considered high-ability kids because the 30% performance compared to the Singapore cohort. They use English as a medium of instruction in schools, and the students were also effectively bilingual. So for study 1, I look at the relations between school achievement and the academic self-concept. So I review evidence from many decades of ASE research. Not many gaps, but found some and tested hypotheses on this group of kids. So I collected data from 2 time waves, and then I get data about their academic self-concept in both the cognitive and affective components in physics, English, and math. And I use SEM and CMA to evaluate the data. And of course, I need to use the instruments from her, right? Because it's so good. So for physics competence, it's something like I am good in physics, and affective is how much they enjoy physics. And as you can see from the high alpha reliability, very good instruments. So the results I get are these. These are not new findings. These are findings from past academic self-concept research from her and his collaborators. So I found that cognitive and affective components are distinct even for these kids. Academic self-concept is domain-specific. That means if they do well in math, then they will have high academic self-concept in math and not so much for English. There's also reciprocal effects. That means if they're good in something like math, and then it contributes to high self-concept in math, and then they will have higher achievement in math as well, in their future achievement. The ID model also mapped for English and math, but physics and math were found to be interrelated. So this is the correlation matrix. As you can see, very high between competence and effect, but later I'll show you the path model showing that they predict different stuff. And then you can see that for English there's is not so much for physics, but then it's interrelated with math. And this is the path model that I found. You can see that that is domain specific because physics will enhance future physics achievement and self-concept, and not so much for English, but there's some effect on math. Okay, we'll look at this later when we have more time. So basically the implications of study 1 is that academic self-concept play a very important role in the classroom. So we need to look at enhancing their self-beliefs in our everyday lessons. So this is the part of effective instruction. As we go through my presentation, you'll see this part many times as I find the essential ingredients and the products coming out of this part. So at the end of study 1, I found that we need achievement and self-concept as good measures of an effective instruction. So move on to study 2. So I look at the psychometrics and investigate the relations between achievement and other factors of motivation. Okay, the method I use is similar with study 1. It's just that for study 2, I added one more time wave of achievement data, which is the achievement in grade 6, the year prior to grade 7. And for the motivation survey, I not only measure their academic self-concept, I also measure their self-efficacy, inquiry, because it's to do with science, so engagement and educational aspiration. So these are the motivation variables from very good validated instruments. As you can see, they all have high reliability. These are the factor correlations. So if you can see from this table, these are all the motivation variables. below in white are all the achievement data. You can see grade 6 achievement data doesn't influence the grade 7 motivation, whereas the grade 7 motivation at time 1 and time 2 are more highly correlated. So what the results and implications shows that these motivation factors can be considered as good outcomes of an effective instruction, and that grade 7 is a good starting point for innovative practices. So that's why my study 3.5 focus on grade 7 for the intervention. So back to the part. So we already have achievement and academic self-concept. Now I added on to look at aspirations, engagement, and inquiry as good measures for measuring an effective education, science education. So now I will start my study 3, element interactivity as a construct for analysis of students' work. Now because study 3, 4, and 5 has to do with element interactivity, I'm going to introduce to you what it means. So element interactivity is to look at the word element. Element is anything that needs to be or has been learned, such as a concept or procedure. So basically, element interactivity is the interaction of these elements. So you experience high element interactivity in your working memory if these elements heavily interact and cannot be learned in isolation. So the more elements interact, the higher the working memory load. And low element interactivity is when individual elements can be learned in isolation and imposes very low working memory load. So now I'm going to let you experience element interactivity in science. So I have got 3 fruits. Lemon, a small tomato, and a large apple. So I'm supposed to measure for you, but due to lack of time, I measured for you, so you can check later at the end of the lesson to see whether they match the numbers. So to help you make a decision, I have written the mass in grams, so 127 grams, 63 grams, and 101 grams. Okay, let's start with lemon. How many of you think it floats? Put up your hand. Okay, so the rest of you think it sinks, I assume. No sitting on the fence. So an effective way to find out whether something floats or sinks is to immerse them right to the bottom, just in case there's air trapped, and then you lift it up. So well done, those who gathered it floats. Now back to small tomato. So if you look at lemon, it's big, 127 grams, and this is 63 grams. So how many of you think this floats? Put up your hand. Okay, now I'd like to ask maybe James, why do you think it floats?
Because it has a sort of a non-porous kind of skin.
Okay, what about me? It's a non-porous.
It's just a feeling.
Anyone else who said it floats? Okay, now let's find someone who thinks it sinks. Herb, why do you think it sinks?
Oh, I don't think it sinks, I think it floats.
Oh, okay, sorry. Who else thinks it sinks?
I think it sinks
Okay.
because of the denseness of it. Just that, because it isn't porous. The lemon has lots of little holes in it which can hold air to make it float. So it's just a feeling again.
Okay, so let's test out those feelings. What about the last fruit? That's right. And Emma, why do you think it floats?
Oh, I don't want to say why. Because you go lobbying for apples.
Ah, okay, that's cute. So, I mean, from this experiment, if you think, oh, little things sing, right? I mean, for a child, like, oh, so little things sing because it happens to be, look, I don't know.
Smaller.
Yeah, small. Okay. So now then, this is Play-Doh. Can you tell me whether it floats or sinks? Anyway, before you say it floats or sinks, I've taken a very little tiny piece here, over here, and then this is a big Play-Doh. Now tell me whether it floats or sinks. How many of you think it floats? from the Play-Doh. Do you think it floats or sinks? How many of you think it floats because it's super tiny? How many of you think it sinks? Okay, let's see. Okay, Matt, why do you think it sinks? This is so tiny.
It's the same material and compound. I didn't think the size would be relevant.
Oh, what a scientific answer. Anyone else? Yannick, why?
I think it floats just to show that little creatures can float as well.
So let's see. Do you see that?
No, it's too small.
Sinks. And Matt has a model answer for that one. Okay, so as I go through the learning styles of floating and sinking, as you can see from the answers you gave, okay, first of all of you paid attention because it's interesting. So you have all motivation. So when you have motivation, you pay attention. And then all of you have got your working memory and your long-term memory. So working memory is when the elements that I introduced to you today, like floating and sinking and the apples and all that, those are like the intrinsic load that you have. And then when you need to make a decision whether it floats or sinks, you need to use your long-term memory. So that's why I asked you for your reasoning. When you give me the reasoning, you recall your long-term memory, experience with everyday life, lessons in science, obviously, and or general knowledge in science. You retrieve it, and then you form new knowledge. So if you retrieve, let's say, the wrong knowledge, and then now you see it, you form new knowledge. So you construct schema, so the next time you face the same problem, you can do the task. So that is the cognitive process that we need to consider. So we can always up the element interactivity. So you will say, oh, it's so simple, just floating and sinking. Then I can ask you to design an experiment. Or now that you see that the tomatoes sink, how can you make it float? You see the apple floating, how can you make it sink? And then the concept of relative density comes in, and then it ups the element interactivity and design an experiment as well. So that goes on to study 3. For study 3, I did not do any intervention, and I didn't analyze the learning task as well. In fact, instead, I analyzed a science problem that the students have to do in class. And then I look at how the students solve those problems, and from the problem-solving processes, I deduce their level of expertise. So this is the problem that I analyzed. So it's a table. It gives you the time interval and the average speed in each time interval. So this is a high element interactivity problem. It looks simple, but it's not, because there's a lot of elements to consider: distance, time, and all the information that's given to you. So this is the kind of solutions that the students gave. This one has got 6 operational lines. So operational line is basically the addition, multiplication, or whatever, and then the final answer is not considered as an operational line. So basically what they did to get that answer for each part of the question. And then this is another child doing the same problem but just using 3 operational lines. And then this child just used 1 operational line. Now looking at the cognitive processes, can you tell me which student has got the highest level of expertise?
The bottom.
Yes, why the bottom?
Just able to collapse all of the concepts into one.
Exactly. So from this, you get to see the child's expertise levels. And all these children got 2 marks for their solutions. So it shows that element interactivity goes beyond test scores, gives you more information about the student. So this is what I found about the operational lines. You can see that most of the students need to use between 1 to 4, only 20% use 4. And then the rest of the kids that do not get full marks, they use like operational lines like 1 or 3, but we can see the element interactivity in each operational line is still low because there's no concepts in their answer. That means they have the wrong concepts. So the implications for this study is that students are still developing their expertise. So even though this is a good school, but they are considered novices in this topic because they have not learned it before. And element interactivity determines problem complexity, so it can be used to guide instructional design. So back to the pot. This is the first ingredient that I found to be very useful for an effective instruction. Okay, study 4 is when I become a little ambitious and implement an intervention, and then I measure the intervention effects on the kids. So the participants are grade 7 students, not many, I just use 156 kids. There's no control group, that means I'm going to use another topic that has no intervention and compare the achievement in both topics. So the intervention topic is density, the non-intervention topic is properties of matter. And the grade 7 science teachers, they'll be implementing the intervention. There are only 4 teachers, but they're experienced and their average age about 35 years old. So the intervention has got 4 phases. The pre-intervention phase is when I did all the pre-tests. So the kids do the pre-test, and then they learn the properties of matter, topic of science, in the regular instruction way. And then they did the post-test for that topic. And then after that, they will do a pre-test on density, which they've not learned. And then also did the pre-test for academic self-concept. And then for the second phase is the teacher acquisition phase. So we need to train the teachers to implement the intervention. So the teachers did workshops on how to design instruction that manage element interactivity. Stage 3 is 7. The kids did the density instruction. By the way, the principle, the properties of matter topic is also taught over the same time frame. So 7 1-hour lessons over 3 weeks for both the intervention and non-intervention topic. So for density instruction, it comprises hands-on and classroom-based instruction, which I have over here if you want to take a look at it later. So it has reduced element interactivity. And the post-intervention, there's post-test on density and self-concept survey, and the post-test for both tests has got similar element interactivity. The post-test for properties of matter and post-test for density. And these are the results. I use a PET sample t-test to compare the achievement and the self-concept scores. So for self-concept, you can see that it goes from 3.77 to 3.98, increases but not significant. And then this one, it increases as well, but not significant. And the highest improvement is seen in density, in which I did the intervention. So implication for this study is that when you reduce element interactivity and manage the every stage of learning, students benefit in terms of higher achievement and maintain academic self-concept. As you know, that adolescents' self-concept normally go down, especially during transition years, grade 7 to grade 12, but I managed to maintain it for this short intervention, which I thought is quite okay. So this is my final study, where I look at the effects of dual approach intervention on achievement and motivation. So I became more ambitious. I did the intervention not only looking at reduced element interactivity, but I also have the motivation aspects to my intervention. So again, I increased the sample size. I included a new cohort of grade 7 students from 11 classes. So I wasn't given a choice for the control and intervention group, they were given to me. So 5 classes was in the control group and 6 classes were in the intervention group. So there's a distribution of boys and girls, and then grade 7 science teachers, 4 of them were involved in the intervention. By the way, those teachers who were involved in the intervention just teach the intervention classes, so there's no overlap of teachers. So these are the items that I use to measure the motivation towards science. So self-regulation, because it is a good measure of FDT. So self-regulation is like, if I do not understand something, what does the child do about it when they do not understand something? They do, like they read the information again, they try to figure it out. Task goal is a measure of giving the reason why they do their work. It's intrinsic motivation, like because they like to learn new things, they want to get better at it, it's important that they do the work well. And ego involvement is a part of extrinsic motivation, is that they want to show others that they're smart in science. And the reason I included ego was because the kids will be working in groups and want to show whether the motivation of doing the learning task is because you want to impress their peers or is it for their own learning. And then I look at inquiry. So basically these items are mostly for like their learning attitudes. Do they like to do investigations or do they prefer the traditional approach where the teachers just tell them what the science concepts are about? Education aspiration and career aspirations, very good measures because you know that is the problem of science education. People don't care about pursuing science in the future. So I'm going to check please. And engagement is when they are attentive, sense of competence and interest is academic self-concept measures which I've talked about earlier. Okay, so for the intervention. So before the intervention, the kids experience heat and forces science lessons and speed and density as well. So the kids have to do all these pre-tests. Now the pre-test, because they have never been taught the topics before, the pre-test questions were very simple with low element interactivity. And the motivation factors I assessed during that time as well. And then they went through the science instruction. So for every topic, like for example heat, before they do heat, they take the pre-test and then they had the lessons on heat and then they do the post-test on heat. After that they do the pre-test for forces and then lessons on forces and then post-test on forces. So it goes in that sequence. So the post-test measures for cognitive post-test, same thing, but for the post-test, now that they have experienced the lessons, we have each test is 10 marks. So 5 marks is low element interactivity questions, so simple. And the post-test, the second part of the post-test is a 5-mark high element interactivity questions. So each post-test as well. And then which I will analyze separate. And then the motivation instrument is the same as the pretest. It's just that the cognitive pretest and post-test are different instruments. Okay, so the control group basically did all these 4 science topics using regular instruction where the teacher just gives the information, they write down notes. For the intervention group, they had regular instruction for heat and forces. But for speed and density, they experienced the dual approach intervention. And each topic took 7 one-hour sessions over a period of 3 weeks. So each topic is about the same time frame. Okay, so this is a dual approach versus regular instruction. So you get to see here I compare side by side, where the student participation is active for the dual approach, they discuss in teams. And then for regular instruction, mostly passive learning. So the learning processes, the dual approach look at both the cognitive and non-cognitive processes. For the cognitive processes, CLT is used to manage element interactivity at each stage of learning. And for the non-cognitive processes, SDT was used to design a learning environment such that it meets the students' 3 basic psychological needs of competence, autonomy, and relatedness as much as we can. And for the outcomes, we look at achievement motivation outcomes, whereas regular instruction just care about their achievements. Teacher's role for our intervention is that of a facilitator, while regular instruction, the teachers just give the kids information. So these are the learning processes of the dual approach interaction. So apart from isolating interacting elements, that means the students will go through the conceptual understanding first through hands-on activities and discussion. It also goes from simple to complex sequencing. That means before they look at floating and sinking as a trigger, they learn more about mass, about volume, how it's represented in an object before they move on to the concept of density, which is more complex. And then the learning tasks are meaningful so that they can recall from the long-term memory and interact with their hands-on activities, and also trying to meet the basic psychological needs. That means for competence, the teachers give constructive feedback to the kids to help them develop their competence, and because it goes from simple to complex, the students get to experience more success in their learning experiences. Autonomy, there are instances when the students are able to make decisions within the learning task, and related as they work as a community. The expected outcomes for the cognitive, we expect improved transfer of knowledge, resulting in higher achievement. And for the non-cognitive, we expect higher motivation and higher self-concept. So these are the results. If you look at the pretest, so both the control group and intervention group has got similar achievement for the pretest. In fact, intervention is slightly smaller, but they are all insignificant. And then for the motivation, they are also similar. And for the ICC, not much difference as well. So basically, the control group and the intervention groups are similar in terms of ability and motivation at the entry level. Now, these are the results for the post-test. This is just the descriptive stats. And this is the multiple regression analysis results for the cognitive side. So if you look at the results for the speed, low element interactivity, no difference. Maybe it's a ceiling effect. It's a simple test, so both groups did similar. But for the high element interactivity on speed, high effect size, and density high element interactivity, also high effect size. And I control for gender and pretest. And for the topics that there was no intervention for both groups, heat and forces, for both low and high element interactivity, there is no difference between the two groups. Now looking at the multiple regression analysis results for motivation. So for self-regulation, there's a significant difference. Task goal as well. Ego, no difference. Inquiry, yes. Educational aspiration, yes. Career aspiration, yes. Engagement, no. Sense of competence, a little but very small, and no difference in the interest.
So this is using time 1 as a covariate and looking at the effective time 2.
Yes.
Sorry, I just...
Yeah, it's okay. Okay. So basically, the intervention group outperformed the control group for the cognitive and non-cognitive. They had higher achievement, higher motivation, higher self-concept. So the intervention effects can be seen, achievement, but only for the high element interactivity problems. And for non-cognitive, we see that the intervention group did better in self-regulation, task goal, inquiry, sense of competence, educational aspirations, and career aspirations. But there's no intervention effect seen in the low element interactivity part of the test. And we also see no significant difference in ego, interest, and engagement. But for interest and engagement, we think it's a ceiling effect because if you look at the descriptive stats, what the control group also say that, oh, I pay attention, I'm engaged, I love physics. So it could be that one. So these are the implications. If you reduce element interactivity and meet students' basic psychological needs in the learning environment, you have positive cognitive and non-cognitive educational outcomes. So now the pot is hot because I put in one very important SDT ingredient, and I'll have more measures of an effective instruction. So summary of results. From my last study, you see that is the study that encompasses all my other studies. So a recap from the first study, you can see that academic self-concept played a very important role to student achievement, and so do other motivation factors. So element interactivity is shown to be a very useful construct to analyze students' cognitive processes, as it informs us of student expertise, it guides instructional design, and even related to achievement. So what are my future directions? So hopefully educators and curriculum planners should consider having the cognitive and non-cognitive aspects of science learning in their everyday lessons, using element interactively to guide instructional design, and making sure students' learning environment includes their basic psychological needs so they can be satisfied to have positive outcomes such as high achievement and high motivation which complements each other. So hopefully we can transform the science learning from this to this. Thank you. Yes, Rose.
Thank you very much. This was really excellent. You have fantastic didactic skills, I must say.
Oh, thank you.
In the last study, you have treated the non-cognitive variables as outcomes, as dependent variables, demonstrating improvement in these variables. And in the first study, you had used the non-cognitive variables as a mediator between pre- and post-achievement. So these are two different viewpoints, and I wonder whether you also tried in the last studies changing the specification and looking at the operating mechanism of achievement change by adding those as mediators or moderators or any other kind of mechanism.
Very good suggestion, thank you. It's not a question, it's a suggestion, right?
Okay.
Yeah. I didn't look at it. Yeah, because study 5, as you can see, it involves a lot of student analysis of 4 topics, so I just did that analysis and not the others.
No,
but
right.
I can look into that now that I have time. Thank you.
That is a good suggestion for the next step of research, because this finds that study 5 is just looking at the intervention effects. We didn't see, well, because the whole point is about the process. So you're talking about the process.
Yes.
So I think that is one thing that we need to look at later on.
If you want to know whether these variables are active ingredients in the intervention, then it might be useful to specify them as mediators.
Sort of following up on that, there is an SDT's rationale to the intervention, but those aspects were sort of confounded. Did you measure, you measured self-concept, which is basically the competence within SDT, but did you look at the other components, the autonomy and the belongingness? Did you measure those to see whether the intervention had an influence on those?
No, we didn't. What we did is we had an intervention fidelity. That means during the intervention, there was a recorder and video recording, and we just make sure that the teacher implemented that, but that's not like a huge component because we didn't measure it. Yeah, just measured out those outcomes.
So you don't know what about the intervention it was that worked?
Yeah.
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 So that's sort of along the lines of what you were saying, but yeah.
But there's a measure of self-regulation, which is, well, not directly related to autonomy, but that gives some indication of how the kids use their own time and their effort in trying to solve their problems. But for relatedness, did we have something like collaboration? We might look at that.
Oh yeah, because we interview the kids. Yeah, so there will be after this maybe I'll work on a qualitative paper, like to work on the teacher interview, student interview. Has so much data for this study. Yeah. Yes.
How did you deal with the clustered sample aspect? Did you use a multi? How did you deal with the fact that you had kids clustered within classes?
Because I think they had low ICC, so I didn't really look at that. I think in my paper I wrote something about that one, that they had low ICC, so the kids are similar
I mean, I understand that you didn't have the luxury of being able to randomly assign, so you sort of had a loose random assignment at the classroom level. But your ICCs were sufficiently low at pretest, so that if you get a reviewer that's asking you that, you can probably say that the ICCs were so low that the clustering effect would be very small,
Yeah.
so that you can get away with that maybe.
Yeah.
Mm.
Yeah.
I want to know what's going to happen with the cans and the Easter egg.
Okay, cool. Good question. I'm glad to do this. Those who can guess whether this teeny weeny chocolate float or sink can get chocolates. So lots of chocolate away you can take them. So what do you think? How many of you think it floats?
Is it a hollow egg or?
No, I don't
That's
know
cheating.
actually.
I think there's one that falls. It's too small to be hollow.
So
You never know what the manufacturers do.
Test it out.
So.
I think it's not going to float.
Right?
Who says it's gonna float? Put up your hand. Okay, so everyone. Okay, just show of hands. How many of you think it's gonna sink? Wow. So Joseph, can you say why you think it's gonna sink?
I can't really say.
So it's a
I don't understand why it was floating and not sinking. I was hoping you were going to finish all that stuff. Like, why is that?
The thing is, Matt just gave a model answer just now, right? Why things float and sink? Matt,
I
try.
can't remember it. I was just in the zone, that's the pressure.
That's it. Run forever.
Yeah.
Equals.
Yes, exactly. That's it. It is a relative density. That means these items float because they are less dense than water. And do you know what's the density of water? Like regular water? It's 1 gram per cm cube. So even though this apple is large and you feel it quite heavy, but it has a density of less than 1 gram per cm cube. Yep. So this one
Is what?
Is it solid?
let's try.
Yeah. Jenna got it right. Jenna got it right.
Let's
Can you
try.
unwrap it?
See that?
Oh.
Yeah. Wow. Why? Because this one has got
That's a hollow one.
yeah.
I'll
This
have
one has
one
got
on
air
box.
trapped inside. You see bubbles? Yeah. So this one I put all the way in, let all the air out, and then it stays. So yeah, it's things. So in Easter chocolates are not hollow.
Yeah.
Yeah, everyone gets one. Yes.
So, is this a test of the quality of the tomato? If it's a dense tomato?
Janet just said about the tomato. Obviously, she has a lot of experience with cooking and using ingredients, and yeah. And they said something about
Eggs or fresh eggs.
SS.
They're supposed to float, right? If they're
No, she said no. Okay, right. Yeah. So bad fruits have a lot of carbon dioxide.
Is bad. Okay, got it.
Yeah. Yes.
What about a soft drink?
Ah, yeah. What do you think float or sink? Yeah, I mean you have had experience putting it in ice water.
Unless you pack it down with ice.
Yeah.
But what would happen if you use proper Coke, not Diet Coke?
Yeah.
Seriously? So what is it that's in the Coke? Sugar. So it actually will sink. Proper Coke.
Yeah.
Proper Coke is zipped.
Yeah, okay.
Ah.
Drink Coke Zero. No sugar. Yeah.
What about Coke Life?
You can try that at home.
I'm not natural sugars.
Not difficult.
I don't know if I'm being healthy or not.
It's a green can, it must be healthy.
All right, do we have any other questions? Because I think the panel has to stay now.
Yeah.
Yeah.